So we're going to look at finding areas under a curve. And so we can find areas under a curve or estimate areas under a curve by making shapes under a curve that we know how to find the area. So we know how to find an area really easily of a rectangle. And so a lot of the times, at least in this class, we're going to use a rectangle to find or estimate an area. So the following states, so find the area of a region R below by, bounded below by the x-axis. Okay, so that's a major piece there too. And we'll talk about area in a minute, but right now we're just looking at area above the x-axis, and it's the area bounded by the curve and the x-axis itself. So find the area of the region R bounded below by the x-axis, on the sides by the lines x equals a and x equals b, and above by the curve y equals f of x, where f is a continuous function on AB, and f of x is greater than equal to 0 for all x on AB. Like I stated, it has to be right now above the x-axis. We'll look at cases where it falls below the x-axis later on, but we'll talk about that when we get to it. So what we're going to do is we're going to subdivide these into n equal triangles, not triangles, rectangles. Okay, so the first step that we want to do is we want to subdivide our interval AB into n subintervals of equal width. And we're going to call that the change in x, triangle x. Okay, so we're going to figure out what that width is that we want. And then we're going to go in and we're going to make that width. So each width in here is the change in x. That change in x, we can figure out what that width is by going in. We can figure out what the length from A to B is, right? And so we can find that length by looking at the bigger x value, B, minus the smaller x value, A, and dividing it into n equal pieces. So that is going to give us the width of each rectangle. So we're going to decide how many rectangles we want. We're going to subdivide it into that many equal widths of our rectangle. So the next step, so second step on each subinterval, we're going to draw a rectangle to approximate the area. Okay, so this is our first subinterval, and we're going to draw a rectangle. I'm going to show you there's different ways that we can draw this rectangle in a minute, but we're going to draw rectangles for each interval. And we could figure out what these heights are of our rectangle by looking at these points on a graph. So this point right here, yeah, that is a point. That could be the height of our rectangle. So in this case, this would be f of, maybe I called this x of 1 here. X of 1 is my height. So here, maybe I can call this x of 2. This height in here is f of x of 2. So I can do that, and I can get the height of each piece of my rectangle. So f of x of I is the height of the rectangle. Let's call it the rectangle I, the ith rectangle in that interval. And so the area of the ith rectangle all that is it's equal to the width, but each width is a change in x times the height. And the height of the ith triangle we can find by f of x sub I. So we can find the area of each one of these rectangles. And if we sum up the area of each one of these rectangles, we're going to have an estimate of the area just bounded under the curve. And so I just mentioned this, but the third step is to determine the area of each rectangle. The width of the kth, they called it the kth, I called it the kth rectangle is triangle x, delta x, the change in x, different ways to say it. The height is, if we look at f of c sub k, the height. And the area of that rectangle is this. A sub k is the height of the rectangle, f of c sub k, times the width, delta x. Okay, so we're going to have to go through and find the area of each one of those, and then we're going to sum them. So fourth step, sum up the areas of the rectangles to approximate the area under the curve. So technically, notice that each one of these areas of each rectangle has this same width. And so we can technically, if we wanted to, write this another way, where we factor out that width of each triangle. So it's the width of each triangle times f of c sub 1, the height of the first, plus the height of the second, all the way out to the height of the nth rectangle, c sub n, yeah. So this is the estimate of the area under the curve. The more rectangles we get, the more accurate we're going to get on that estimate. Okay, so the height can be done in multiple different ways. One of the ways is called the upper sum. And so what we're doing for the upper sum is that you're going to split up your rectangles into different rectangles. And the upper sum, it's the point ck f of c sub k, which is the absolute maximum of y equals f of x on that kth subinterval. So for instance, if we were to look at the second piece in here, we're going to the height, the highest height on this curve right in here. Well, the highest height on that curve right there is this point right in here. Notice that first interval, this is the highest point on that curve for that rectangle. Where if I'm looking at this one, the third one, that would be at this endpoint is the highest point. It's the highest point on the next one, and we can continue on. For this rectangle right here, this is the highest point. This one's the highest point. And so we're getting the height by looking at the highest point of that rectangle. And that's the upper sum method. The lower sum method is where we're going to look at the smallest value or smallest height that that rectangle can be. So the lower sum, if we were to look at it this way, You're gonna look at your point. It's the absolute minimum of y equals f of x on that kth interval. So for this first interval in here, the lowest point on that graph in here, that lowest point is right here. The lowest point on that graph for the second one is right there. Lowest point. So we're trying to find that smallest point for each rectangle. And that's what we would use for the height. The other one is looking at the midpoint. And so this is where you have some sub-interval. And you're just taking the midpoint in between those values. We have the left and the right endpoint method also. And these are more the ones that I use are the left and the right. So in the right hand, you're just looking at the far right hand part of that each rectangle, and that would be the height that you would get. And then the left endpoint method, you're going to look at the left endpoint of each rectangle instead, and that is going to be what you use. So it really doesn't matter which one you determine to use. It's all going to give us an estimate. Some are maybe a little better than others, depending on the shape of the graph. But the more rectangles we get, again, the better accuracy that we're going to get. And then it really doesn't matter, because basically we're going to be using limits. We're going to take that number in of rectangles to go off to infinity. So we're going to get an infinite number of rectangles in there. And if we do that, guess what happens? So there's one line, right? We're just going to fill this up is what our whole goal is. And that would just give us the exact area under the curve. So that's the goal. And I don't think we're going to get to that until Monday of next week. We'll see.
Is this stuff, oh, sorry. Is this stuff going to be on the chapter 4 test or no?
No, so this would not be on that chapter 4 test. So this is we just started chapter 5. Antiderivatives will be on that chapter 4 test though. Okay, so let's look at an example. So we're going to use finite approximation to estimate the area under the curve y equals, or f of x equals 3x plus 1 on 2 to 6 using the lower sum of the 4 rectangles of equal width. Okay, so let's first graph this. And this one isn't bad to graph. And we can see that that's just a line. We can see that the y-intercept is at 1. And if we graph this, let's see, basically rise 3 run over 1. Let's just go over. So let's see, 1, 2. We're starting at 2. So let's just find the point at 2. So 2, that would give us 7. 19. Okay, there's 19 values. I might need to make this a little smaller in here. Okay, so 1. So we had again a point at 0, 1. When x is 2, we're going to get back 7. When x is 6, the last one, we would get back 19. Why my stuff is not dragging. Okay, I'll just try to make the line without that. Okay, so my line looks like this. We're starting here at 2. We're going to 6. And we're trying to find this area in here. And it wants 4 different rectangles. So we need to figure out what the width of each rectangle is. And we can do that by looking at the change. What's the distance? 6 minus 2 all over how many we want, which is 4. So this is 4 over 4, which is 1. So I know the width of each piece is 1. And it wanted us to do, what did it say? The lower sum. Okay, so this is the first rectangle, lower sum. The smallest point on this rectangle is here. So the area of our first rectangle is going to be the width, right? Which is 1, all times f of that smallest point is 2, f of 2. So that's area of the first one. Might as well just do it. So this is 1 times f of 2. If we plug in 2 into our function, we saw that that was 7. So this is equal to 7. So now if we looked at it and we looked at the area of 2, the width is still 1, but the height, we're going to look at f of 3 because we want the smallest in there. So if we plug in 3 into f of x, we get 3 times 3 is 9 plus 1 is 10. So we have 1 times 10, which is 10. The area of the third rectangle, again, our height, or not our height, our width is 1, but the lowest point for that rectangle is f of 4. And so we can figure out what f of 4 is by plugging it in. So that gives us 13. So 1 times 13 is 13. And then the last one. So the height would be f of 5. Width is 1. But f of 5, if we look at that, plugging that in, we get 15 plus 1, which is 16. So 1 times 16 is 16. So this is our estimate, what is shaded in black. And so our area, our estimate of our area is approximately 7 plus 10 plus 13 plus 16. So 17 plus 13 is 30. 30 plus 16 is 46. I don't know what my units are, but if it had given me my units, I would put that. Area would be units squared.
So 6 isn't included in that?
Did I not do 6? No, it's not. So that's not part of our height. So we wouldn't look at f of 6 because this one wanted us to look at the smallest endpoint of each rectangle. So you were talking about, right, this plugging in 6 in there, f of 6.
Yeah.
Yeah, so we wouldn't, in that case, if we were doing the upper bound, we would have done f of 6, f of 5, f of 4, and f of 3, and we wouldn't have looked at f of 2. And that would have given us you can see that will give us an overestimate of our area, where what we just did gave us an underestimate of our area. Technically, we could find the exact area of this, right? We could find the exact area of this by using a triangle. We could look at technically this big triangle in here, figure out what that area is, and subtract off this smaller triangle in here. And that would give us the exact area. Okay, so let me pull another example. So our next example is find the area under f of x equals 1 over x over the interval 1 to 9 using 4 rectangles. And we're going to use right-hand endpoints to find the height of the rectangle. So again, it's helpful to kind of graph the graph of 1 over x. Well, I know I have a vertical asymptote at x equals 0, and I have a horizontal asymptote at y equals 0. I guess I can plug in points if I wanted to, but I know at x equals 1, I have 1. At x equals 2, I'm going to have 2. I'm going to go out to 9. So, but I should make my things more equal. Okay. Not to scale, but we have this curve. That looks like this. We want to figure out what the width of each rectangle is going to be. So 9 minus 1 all over 4. So 8 over 4 gives us 2. So we're starting at 1, but we want to go over 2. So the first one is right here. So the right-hand endpoint, right, that length is 2, is actually x equals 3. So it's going to be 2 times f of 3, which is 2 times 1 over 3, or 2/3. So we're going to go out another length of 2. But if we go to 2 there, the right hand is going to be at f of 5. So the area of 2, width is 2 times f of 5. Well, that's 1/5 times 2 is 2/5. We're going to look at the area of the third rectangle. Again, we got to go out a width of 2. So going from 5 to now it's 7. So it's 2 times f of 7, which is 2/7. And one more. So going another distance of 2, we're getting to 9. So we're going to look at 2 times f of 9, which is 2/9. So to get the area, approximate area, we would add those all up. So we're adding 2/3 plus 2/5. I'm going to leave room to get common denominators, plus 2/7 plus 2/9. Okay, what is our common denominator? It's huge. It would be 9 times 5 times 7. Oops. So 315 is our LCD. So I'd have to multiply this first fraction by 105 over 105. So doing that, 105 times 2, that's 210 all over 315. Plus, so let's multiply. So 315 divided by 5, that's going to give me what I need to multiply by, and I'm 315 divided by 5. That is 63. So we're going to multiply both the numerator and denominator by 63. 63 times 2, that's 126 all over 315. So figure out what we need to multiply 7 by to get 315. So 315 divided by 7, that will give me the number, which is 45. So I'm going to multiply this by 45 over 45. So 45 times 2, that's 90. So you have 90 over 315. 9 goes into 315 35 times. So we're going to multiply 2/9 by 35 over 35. So that gives us 70 plus 3/15. 70 over 315. Okay, so summing up our numerators, 210 plus 126 plus 90 plus 70. So that's 496 over 315. Which is 1 and 181 all over 315. So this is approximately what the area is, whatever unit squared is. So each time it was a right-hand endpoint. So this looks like an underestimate. And again, my thing is not to scale. This would actually be higher. And so we get something that looks like that is what we found the area of. So we're going to estimate the area of f of x equals 4 minus x squared on the interval between -2 and 2 using 2 rectangles, and then we're going to use 4 rectangles. And if you look at this, the graph of f of x equals 4 minus x squared, that ends up being a semicircle. It's above the x-axis. Radius is 2. So it looks like this. And the first one wanted us to use 2 rectangles. So if we use 2 rectangles, let's find the width. I can already tell what it is, but let's just do it anyway. So 2 minus a -2 all over 2. So 2 plus 2 is 4. 4 over 2 is 2. Let's use the right-hand endpoint, RHE, right-hand endpoint. If we use the right-hand endpoint, that would mean that we have a height here. So the area of the first rectangle, well, the width is 2, all times the height of f of 0 Oops, something's off. So that is not a semicircle, is it? Because if I let x equals 0, that's going to be 4. Here, this is why I think it was I was thinking of the square root. I'm wrong. What was I thinking? Let's go back. This is a parabola upside down. Vertex is at 0, 4. I was thinking of square root. Y equals the square root of 4 minus x squared. We just did that earlier today. So let's see. The height is 4. We still have a point at -2. If we plug that in for x, you get 0. +2, plug that in for x, we get 0. So we have 2 times f of 0. F of 0 in this case is 4. But if you look at that, okay, that would give us back 8. The thing is, when we look at the right-hand input of the next one, notice that that's at the x-axis. And so if I look at that rectangle, that's just that line. So the area of my second rectangle is 0. So area is approximately 8 units squared. Where if we did this and it says use 4 rectangles, our width of each rectangle is going to be 2 minus -2, but this time we're dividing by 4. So 4/4, which is 1. So we have this time 4 rectangles. So the first rectangle, the height is at -1. So the width is 1, but the height is f of -1. You plug in -1 into our original function, f of x equals 4 minus x squared, you get back 3. So 1 times 3 is 3. So the next height, we would look at the area of this rectangle 2. We're looking at f of 0. So 1 times f of 0 is the height. So 1 times 4, which is 4. The third, again, width is 1. We're going to look at f of 1 for the height, which ends up being 3. So we get back 3. And the last one, that's at f of 2, but that's 0, and 1 times 0 is 0. So our estimate, summing those, it's 3 plus 4 plus 3 plus 0, which gives us back 10. So just kind of reviewing sigma notation, just so that when we jump into this next week, that the next part will be easy or easier. So remember sigma notation, basically this bottom number is where we're starting. This is the value you're plugging in wherever you see a K, and you're summing up the number until we get to here, 2. So here we want to look at plugging in 1 wherever we see a K. That's the first thing we're doing.
Is this 5 point or yeah, 5.2?
Yeah, so this is the start of 5.2. And then we're summing plus. Now we're going to go into this function. We're going to plug in 2 wherever we see a K. So if we do that, we can simplify. 6 times 1 is 6 all over 2. Plus 6 times 2 is 12 all over 3. So this gives us 3 plus 4, which is 7. So the summation from k equals 1 to 2 of the function 6k all over k plus 1 is equal to 7. What if you had k equals 1 to 5? Of sine of k times pi. So we got to go in here. We're going to be summing 5 different things. When k is 1, when k is 2, when k is 3, when k is 4, when k is 5. And so we got to plug those in. And so we got sine of pi times 1 is pi, plus sine of 2 pi, plus sine of 3 pi, plus sine of 4 pi, plus sine of 5 pi. Okay, well, that one is not too bad at all. Recall 5 pi. Sine is on the unit circle, your y value. So if I was to look at pi, that's right here, that's 0. If I look at 2 pi, that gets me up to here, that's 0. If I look at 3 pi, that's just another rotation. That's giving me back to the negative. So I'm just adding 0 5 times. Each one of those is 0, which equals 0. In this, we're going to rewrite this in sigma notation if we can. So let's say you had had the following. It said we're going to add 1 plus 2 plus 3 plus 4 plus 5 plus 6. And then I wanted us to rewrite that sum using sigma notation. So we're starting at 1 and kind of look at what the pattern is, right? This k equals 1. Well, basically, I'm just plugging in each integer from 1 to 6. So I can just have k here to 6. Where if it asked us to sum 2 plus 4 plus 6 plus 8 plus 10, gotta think about, okay, what are we doing to get from 2 to 4, 4 to 6? So I can think of it as adding 2, or I can think of it as 2 times k. So if I add, or if I multiply by 2, 2k, the first number we start with would be 1. The last number, though, that we're ending with to get 10, 2 times 5 is 10. So we're going to stop here at 5. One more. Let's say it was 1/2 plus 1/4 plus 1/8 plus 1/16. So we need to figure out what's going on there. Well, if we multiply, let's see, by 1/2. Okay, what about this? This looks like 1/2 to the first power, 1/2 squared, 1/2 cubed, and 1/2 to the fourth. So this looks like the formula 1/2 raised to the k power, where our sum is starting at k equals 1 and ending when k is 4. Okay, so you should be able to figure out what the sum is given the function and how many you're supposed to add. Or you should be able to go opposite direction. Given a sum of things, rewrite it in summation notation. And just remembering that kind of stuff is just going to help us when we jump into the piece where we're looking at these limits. We're going to have an infinite number of areas of rectangles that we're going to be summing. And that's what we were doing in that last piece. We were keep on adding these rectangles. And so we can write that as summation notation.